During a routine pre-flight walk around in 2021, ground crews examining a flyable Boeing B-17 made a severe structural discovery. The left wing had shifted away from the fuselage by approximately 2 inches. This massive displacement contradicted the documented maintenance logs and previous structural sign-offs. The aircraft was immediately grounded. This single discovery triggered a fleet-wide crisis for all surviving airframes. Among them was Boeing B-17, G serial number 4-85718. Originally delivered near the end of World War II and later known as Thunderbird, the bomber belongs to the Mid-America Flight Museum. After its sale in 2020, it was ferried to Madras, Oregon for inspection and restoration work at the Erickson Aircraft Collection and the Warbird Shop. The dry inland setting helps reduce exposure to constant coastal moisture, but it does not replace formal corrosion control, inspection, cleaning, sealing, approved maintenance procedures, or the need to verify fatigue hidden inside primary structure. After the severe wing attachment failure was reported, the Federal Aviation Administration issued a new interim airworthiness directive, effective June 1, 2023. The mandate applied to Boeing Model B-17E, B-17F, and B-17G airplanes on the U.S. register, and it immediately affected the small group of aircraft still flying or capable of returning to flight. Its purpose was to force a more reliable reassessment of the wing terminal-to-spar chord joints. The primary operational constraint was not simply that the wings were aging. The fundamental problem was that the earlier 2001 inspection regime was no longer considered reliable for cracks hidden inside the steel fitting within the spar chord tube. Those older rules included visual, bore scope, dye penetrant, and eddy current steps. But the newly reported failure showed that the accepted procedure still could miss the most dangerous blind cracks deep inside the joint. The critical attachment point consists of steel terminal fittings nested inside aluminum spar chord tubes and held by close tolerance bolts. Because the joint cannot be cleared by surface evidence alone, the 2023 directive allowed 2 inspection pathways. One that separates the joints for magnetic particle inspection of the steel terminal fittings and eddy current inspection of the aluminum spar chord, and another that uses eddy current bolt hole inspection on the steel terminal fittings and the aluminum spar chord. These non-destructive methods still require access, calibration, clean geometry, and approved technique. Their purpose is to detect cracking or corrosion in critical areas of the joint, not to produce a perfect three-dimensional map through every layer of metal. Implementing the inspection and restoration work at Madras required access to the innermost sections of the wing roots. This area is the critical junction where the aerodynamic lifting loads of the wing transfer into the fuselage structure. Some FAA inspection paths can begin with bolt hole access. The larger restoration path at Madras went much further, clearing interior structure, removing panels, and exposing the spar assemblies so the team could inspect, repair, and ultimately rebuild the affected structure. The process is slow and highly constrained by the tight geometry of 1930s engineering. The stakes for this procedure are absolute. A clean finding may satisfy a specific approved inspection pathway, but it does not automatically return an airplane to service by itself. Any cracking or corrosion found in the wing terminal to spar chord joints must be repaired before further flight by an approved method, and the inspection results must be reported so regulators can evaluate the fleet-wide risk. Inspection and teardown on the bomber led to the heaviest possible maintenance path. Public project updates identify major structural work on the inner wing spar tubes, with the restoration moving from normal flight line maintenance into a full IRAN inspect and repair as necessary rebuild. The separation reported on another B-17 had shown that the issue could not be treated as a single isolated defect. For this aircraft, the work at Madras meant specialized technicians had to decouple systems, open the wing structure, address corrosion or structural deficiencies, and prepare the inner wing panels for major spar tube replacement. The engineering team recognized that locating the hidden damage was only the opening phase of the recovery. The compromised steel fittings were integrated into the primary aluminum spars, so any repair had to reach the core of the load path rather than the outer skin. The scanning data confirmed active, hidden fatigue at the bomber's most critical junction, forcing the team toward structural removal instead of surface repair. Faced with verified structural risk, the team encountered a hard engineering limit. A cracked or corroded wing terminal-to-spar chord joint cannot be treated with a casual field patch. Any repair must follow an approved engineering method before further flight. Welding a fitting in place, cutting open the encasing tube, or adding an improvised external strap would create unapproved load paths and could shift the immense shear and bending loads into surrounding vintage structure. For this aircraft, the accepted path became replacement of the affected spar tubes rather than a localized splice. The engineers had to accept a drastic maintenance outcome. The compromised steel fittings required the complete removal of the surrounding aluminum spar cord tubes. This forced a total transition from a localized inspection task to a massive structural extraction project. The main spar is not a superficial component. It is the core physical spine of the inner wing panel. Removing it requires dismantling the primary integrity of the wing itself. Thousands of rivets must be meticulously drilled out, and thick external skin panels must be carefully separated to access the deep interior of the root. Once hidden structural failure is verified and disassembly begins, how can an engineering team source replacement load-bearing geometry when the original factory has been gone for 80 years? To restore the compromised core of the heavy bomber, engineers faced a rigid dimensional constraint. The replacement spar tubes had to match the historical Boeing geometry closely enough to carry the same loads and align with surviving wing structure. Public project updates identify each tube as an approximately 26-foot tapered aluminum extrusion built to original Boeing 1930s engineering drawings. This was not a job for standard commercial pipe. The taper, the alloy, the heat treatment, and the final dimensions all had to be controlled under approved quality requirements, so the new parts would behave like aircraft structure, not industrial stock. The reason is simple. The spar tube is part of a load path, not a decorative sleeve. A uniform modern tube might be stronger in one place and wrong in another, adding dead weight, changing stiffness, and pushing stress into surrounding vintage structure. The surrounding ribs, fittings, skins, and bolt holes also require tight alignment. Even minor dimensional error can make the rebuilt spar impossible to mate with the fuselage attach points. Because the exact manufacturing details are proprietary and not fully documented in public sources, the safest description is this. The tubes were reproduced as certified tapered aluminum extrusions, approximately 26 feet long, using Boeing drawing data and modern aerospace quality control. With the physical geometry requirements locked, how does a team extract the core spine of a massive wing without the surrounding structure losing its alignment? The extraction phase introduced an immediate risk of geometric distortion. A B-17 wing panel is a built-up structure of spars, ribs, skins, stringers, fittings, and close tolerance fasteners. Once the spar tubes and surrounding truss structure are opened, the team must preserve alignment rather than assume the wing will hold its shape by itself. Even a small twist can move historical rivet holes and attach points out of position. To prevent that damage, the restoration team at Madras placed the inner wing panels in custom-built jigs based on original Boeing production tooling. The jigs support the structure, hold critical stations, and preserve the geometry during disassembly and reassembly. The fixture cannot simply force the wing into a convenient shape. It has to hold the surviving structure in the correct alignment while technicians remove panels, drill rivets, separate spar components, and prepare for new tube installation. Once the geometry is locked in the custom cradles, the invasive work begins. Technicians remove original-style rivets and fasteners carefully, avoiding unnecessary enlargement of historical holes. Panels and components are mapped and tagged so they can return to the same structural relationship during reassembly. During this prolonged open phase, environmental control comes from hangared work practices, corrosion control, cleaning, inspection, and protective treatment, not from climate alone. Madras is dry, but the restoration record still shows corrosion work in the fuselage and other exposed areas. The safer engineering assumption is that every exposed surface must be inspected, protected, and documented while the aircraft remains open. With the structure open and held in its fixtures, the actual extraction of the spar components demands strict spatial discipline. Public updates confirm that the rear spars were secured in specialized fixtures while technicians removed the upper and lower spar tubes for replacement. The exact shop choreography is not fully documented in public sources, so the scene should stay focused on the verified constraint. The old tube structure had to be removed without damaging the surrounding truss, rib stations, and attachment geometry. Once the spar components were out, the surviving framework depended on the external jigs to preserve alignment until the replacement tubes could be fitted. Once the airframe is safely secured in custom fixturing, will the team attempt a localized patch on the remaining structure, or commit to a complete teardown of the aft sections as well? The engineering team faced a definitive operational crossroad regarding the surviving inner wing structure. Public project updates identify the rear, or aft, spar tubes in both inner wing panels as the component selected for complete replacement. The team weighed localized repair against long-term structural integrity and determined that for those rear spar tubes, replacement rather than repair was the viable engineering path. This should not be overstated as a confirmed replacement of every forward and aft spar tube in the aircraft, unless a project engineering record states that directly. This replacement path immediately triggered a major supply chain bottleneck. Because the structural blueprint demanded specialized tapered aluminum extrusions, the team could not acquire off-the-shelf commercial components. After extensive research and vendor outreach, the project identified a British aerospace supplier capable of manufacturing aircraft-grade extrusions for the task. The work required custom tooling and production, a process that took over 2 years. What should remain off-screen is any claim that the factory reverse-engineered every detail from scratch or recalibrated every machine to mimic 1940s production, unless the project releases that level of manufacturing detail. During this extended tooling and production period, the open wing structures remained in stabilization fixtures while the team waited for replacement components. The administrative burden matched the physical challenge. The new tubes had to be produced as certified aircraft parts under approved engineering and quality requirements, with material, dimensions, and workmanship controlled tightly enough for an airworthy rebuild. The public record supports certification and quality control. It does not publicly document a separate approval of every tooling parameter or metallurgical formula before extrusion. Following the successful tooling development, the British facility initiated the final production run. The process was meticulously controlled, and the output yielded exactly 8 certified spar tubes. Before clearance for international shipping, these newly minted components underwent comprehensive non-destructive testing. Technicians scanned the full length of each tube to guarantee absolute material continuity. The 8 extruded tubes were subsequently shipped across the Atlantic and delivered directly to the restoration facility in Oregon. The arrival of the new extrusions marked the critical pivot from structural extraction to active rebuild. Restoration technicians unpacked the massive components, conducting immediate dimensional verifications. They utilized micrometers along the entire length of the tubes, confirming that the constant external diameters perfectly matched the tight tolerances demanded by the surviving vintage wing ribs. The complex internal taper had been successfully replicated, securing the necessary load-bearing capability without introducing dead weight into the wing. The team could finally begin the precise process of threading the new structural spines back into the hollow airframe. Beyond returning the heavy bomber to airworthy status, what specific physical history of this individual airframe will survive the rebuild? Examining the forward fuselage of the heavily modified aircraft reveals non-standard nose glazing and additional lower nose window cutouts from its post-war survey career. These features sit outside the standard wartime B-17G combat baseline. The procedural challenge facing the restoration team is how to handle a permanent physical deviation from the 1945 factory configuration. When the airframe transitioned to the Mid-America Flight Museum in 2020, the primary wing spar work demanded strict structural conformity. The fuselage, however, presented a different curation problem. How much of the aircraft's IGN survey history should remain visible? The bomber never saw wartime combat. After factory delivery near the end of World War II, the military placed the aircraft into storage. In 1947, it entered French service with the Institut Géographique National, or IGN. For decades, the agency operated the heavy aircraft as an aerial survey and mapping platform under the civil identity F-BEEC. That civilian career explains the custom plexiglass nose and additional window cutouts documented on the aircraft. It is safer to describe these as IGN-era survey modifications. unless a drawing or maintenance record identifies the exact number, camera layout, date of installation, and reinforcement pattern. In vintage aircraft restoration, organizations often face a difficult institutional choice. One path is wartime reversion, removing post-war civilian modifications and rebuilding the airframe to resemble a combat-era configuration. For this specific bomber, earlier public updates indicated no plan to return the nose completely to standard B-17G form. A later restoration update, however, stated that no final decision had been made on whether to retain all IGN features, although keeping them remained under consideration. That uncertainty matters. The French survey modifications are not random damage. They are evidence of the aircraft's survival after the war. The reason this bomber escaped the post-war scrap drives was its utility as a civilian mapping aircraft. A careful script can preserve the dramatic point without claiming a final official decision. The restoration team must balance structural airworthiness, historical presentation, and the aircraft's long post-war identity. Implementing any conservation strategy will demand precise handling during final assembly. If the IGN-era nose features are retained, the team will need suitable glazing, careful sealing, and approved structural treatment so the aircraft remains weathertight and airworthy. The final surface finish and markings must also account for whatever configuration is selected, rather than pretending the post-war survey history never existed. The completion of this complex restoration would produce a unified but layered timeline machine. Deep inside the wing roots, new certified tapered aluminum spar tubes will restore the load path to approved geometry. At the same time, the forward fuselage may continue to display visible evidence of its French aerial mapping career. When the rebuilt aircraft eventually returns to the active flight line, it should carry not only the appearance of a wartime flying fortress, but also the physical proof of how this individual airframe survived long after the war.